Hello everyone, welcome to our 25th meetup. Today we are going to talk about artificial intelligence for medical treatment. So first, let me quickly introduce myself. My name is Dovydas. I'm currently the president of the Artificial Intelligence Association of Lithuania. Also, I'm a machine learning team lead at Vinted. I'm also founder of Tribe of AI, machine learning and AI learning community. Finally, I'm a lead data scientist at Turing College. So let me tell you about our agenda for today. First of all, I'm going to do some community updates. Then after that, we are going to move to the presentation, Artificial Intelligence for Medical Treatment. By the way, this is our first medically AI in medicine themed presentation and the final one. All of these presentations are based on Andrew Ng's course, like Artificial Intelligence in Medicine Specialization. And so this is today's this presentation is covering the third course in this specialization. So actually I had so much fun doing the course, so I decided to go ahead and do presentations inspired by the course. And finally, at the end, we are going to have the networking part. Networking is, of course, pretty difficult while we're doing all these presentations online, but usually I get one or two interesting questions at the end. By the way, you should be seeing the link to the questions at the end. So if you have at any point in the presentation, if you have any questions, go ahead, write them down there, and later while we are after the presentation and during the networking part, this is the best way for us to communicate and interact. So let's continue community updates. So actually we have quite a few updates today. So first of all, this is our first joint meetup by Artificial Intelligence Association of Lithuania and Tribe of AI. Big applause. Fortunately, it's only I am being recorded, but I really hope that you're clapping at home. We really hope that this new format of some meetups being organized by Artificial Intelligence Association of Lithuania and some organized by Tribe of AI is going to be fun, and we can achieve I think a lot more if we collaborate and do these presentations together. Then I have an update from machinelearningconf.eu. They are organizing machine learning conference mainly targeted for software developers. I actually talked a little bit with them, and they really have top-notch speakers, people from Microsoft, people from Hugging Face, a lot of famous members from the community. And they also invite you, if you want to take a shot at being a speaker. They are also looking for speakers. So if you have some machine learning experience and you would like to share your topic, reach out to them. We might even get a few free tickets. So keep an eye on the information, and I'm going to post in the Tribe of AI platform. If you get these extra tickets, maybe organize some kind of lottery or raffle, and somebody will get the free tickets. And by the way, I don't have them yet, so I just hope that I'll manage to get them later. In addition to that, on Thursday we have this Lithuanian conference, Dirbtinio intelekto Competencies Lietuvoje. By the way, I am going to participate in this one. I'm going to be a speaker. I'm going to do a short, like, by the way, all the presentations are going to be really short, and we will have a discussion, an hour-long discussion at the end. So discussion is usually the interesting part. My presentation is going to be, by the way, again in Lithuanian, efektyviausi būdai įgyti dirbtinio intelekto kompetencijas. I'm going to talk, of course, about the thing which I know best, how to learn artificial intelligence. Next thing is Artificial Intelligence Association of Lithuania. So as you might, even the last time and today, I said that I'm the president, and we are doing quite a bit of member expansion. We are looking to increase the number of members. Previously, the association had a really strong core, but now we are forming an extra layer of members around this very, very strong core. So if you would be interested in joining the association, please follow the link, fill your registration, and we will consider your application, and if you're successful, we will invite you to become a member. So by the way, being a member gets like a very unique set of benefits. First of all, you will be invited to like an exclusive Slack channel. We also invite you to participate in various events and work on, interesting projects. So it's quite an interesting extracurriculum activity. So if you want to be part of that, please apply, become a member of the association. One more thing, Tribe of AI is also looking for new members, more specifically for mentors for the AI Academy. So maybe you are a machine learning specialist who has experience and wants to help the next generation. If that's the case, let's talk. And again, this is a form which you have to fill, but after filling the form, I'll invite you to a chat, and we can talk about I'm looking for mentors who will help the new classes, new teams to get their machine learning skills, to mentor them, to steer them in the right direction. So this is if you're interested in this thing, again, fill the form, and I would be really grateful if we had more members of the community who are active mentors of AI Academy. One of the really exciting things, I guess, save the best one for the last, is Turing College. By the way, one new thing in my already busy schedule is Turing College. So I mentioned that I'm the lead of data science in Turing College, joined them really recently. I'm advising them on the data science course. So if you remember, previously I said that I'm going to do the Artificial Intelligence Bootcamp 2.0. So last year I was doing the first bootcamp. This year I was planning to do the second bootcamp. However, I decided to join forces with Turing College. These are really great people, have a strong vision, and again, much more resources than I had. So I kind of wanted to contribute to the part which I know most about. That's building curriculums, building courses, and I am helping them to build the best data science course in Lithuania. So if you're looking, if you're seriously considering becoming a data scientist, a machine learning engineer, so definitely check out your course. We're working really hard to make this course unique and super good. And so I guess we have to update my previously I mentioned that in all the previous presentations I mentioned that we are doing a bootcamp. So bootcamp has a spiritual successor, Turing College data science course. So we have only the 3 other parts remaining. And regarding the meetups, I guess that's pretty clear. Today we have one. Next month we are going to have one more. Most likely it's going to be another joint meetup with like Artificial Intelligence Association of Lithuania, and I'm really looking to have more diverse range of speakers than just myself. In addition to that, AI Academy has just started three new teams, so really excited about that as well. Really happy that AI Academy, even after like, I think this month is going to be our 2-year birthday, so it's already been 2 years for the AI Academy, one of the staple things for Tribe of AI. Finally, the newest member, our platform. Really happy that the platform is like receiving more and more attention. People are more and more active on the platform, especially in private team channels, and I really hope that this is going to be the central hub for your AI learning. So that's very quick introduction, the update from the community. Now it's time to go for the main thing for today: artificial intelligence for medical treatment. By the way, previously we had two other presentations. We had artificial intelligence for medical prognosis. Yeah, I guess we are back. Sorry, some technical difficulties. By the way, super weird because it was starting fine. Now we had some issues. So hopefully everything's back fine. I need a second to get back to my setup. Yeah, I think I'm good. So I'm not sure which part you missed. I think you missed maybe the whole thing. So therefore, just really, I guess, like double time version, double the explanation speed. So the plan for today is first talk about the treatment effect, the estimation of the treatment effect. The second part will be medical question answering. I'm going to talk about like what's the difference between regular question answering, medical question answering, what is used in the industry. Then I'm going to tell you about the interpretation of machine learning models. By the way, this part is like really similar in both medical and non-medical images. Then just a short list of resources, and finally the Q&A. So let's start for the second time, treatment effect estimation. So the treatment effect estimation is the part where we measure how effective is our treatment, and we have to know quite a bit of stuff to be able to do that. So the first thing which we have to know is the absolute risk reduction. So to calculate the absolute risk reduction, first of all, we have to split our patients into two groups. So we have the treatment group or treatment arm, and we have a control group or control arm. So these two arms, so the treatment arm, I guess, obviously is going to receive the treatment, and the control arm is either going to get the placebo or we are going to get the standard of care. So this one depends on are you solving, I don't know, are you trying to cure a disease which has no cure so far, or nothing really works, or are you trying to solve a disease which has alternatives and you're trying to beat the best alternatives? And the absolute risk reduction is just the difference between the absolute risk in the control group and in the treatment group. Let's continue with the vocabulary. You have to know quite a bit of these like working parts or working facts. So the second one is randomized control trials. So randomized control trials pretty much means that you are randomly allocating subjects into control and into the treatment groups. This helps us prevent the selection bias, so the characteristics of the control group and on the treatment group are the same. So let's say if you're, I don't know, trying to create a cure for heart diseases, and you don't want to have in your control group only young and healthy people. You want to have the same distribution in the control group and in the treatment group, and therefore you are randomly selecting them. And the p-values, we are also using p-values here, so pretty much this is the probability that you have your treatment has no effect. So you can calculate this probability if you're properly doing the randomized control trial. Number needed to treat, that's very simple. That's again very simple. That's just the number of people you need to treat to benefit one, and it happens to be the reciprocal of the ARR. Then we have a causal inference. So this one is what is the effect of a treatment on a patient. So you can have, let's say you're treating a heart attack, and let's say you have a patient, you have provided the treatment, but your patient still got a heart attack. And you would estimate that without treatment, your patient wouldn't get a heart attack. So that would be you are actually doing harm with your model. So there are three states which you can do. You can have no effect, your treatment can have no effect, it can have benefit, or it can do harm. And we are using, by the way, it might be hard to believe, but you cannot have no treatment and treatment for exactly same patient, because you have to choose. So either you do the treatment or you don't do the treatment. So therefore, you have to use some kind of model, how to estimate, how to compare, what's your treatment, what's the effect of your treatment. And you can use Neyman-Rubin causal model. By the way, this Neyman-Rubin causal model, it's when it's shortened, it's just Rubin causal model. So from what I read, Neyman was just a person who came up with this model way before Rubin, but didn't explore it too much. As so happens a lot, it was in his master's thesis, and Rubin was the guy who developed the model. So therefore, for a long time, it was Rubin causal model. The next thing that you have to know is the average treatment effect. So your expectation, it's pretty much your expectation of the difference in the outcomes. So your expectation in the difference with treatment and in the control group. So let's say you're doing a very long treatment, and you're doing a very long trial, and you expect some of your non-treatment group to get heart attacks, and you expect some of your treatment group to have heart attacks. And so these differences, what your average treatment effect is, your expected values for both of these groups, and the difference of them is your average treatment effect. By the way, just so happens, average treatment effect is just the minus ARR, and that's how you have these factual outcomes versus counterfactual outcomes. So what this means is some of the outcomes are not directly observable, so those are counterfactual, and you have to estimate them, therefore the expectation. And the outcome that is observed is called the observed or factual outcome, and the one which is not observed is called the unobserved or counterfactual. What's more interesting than ATE is CAT, and the CAT is conditional average treatment effect, so it can depend on various conditions. So for example, let's go back to the heart attack example. We can have the average treatment effect for people on a certain, like, who have a certain age, or for smokers, or for men, or for women. And you can like, based on this condition, calculate maybe your drug really works well for smokers, doesn't work for anyone else, but it's still a great drug, right? If you can, like, target smokers and reduce their risk of heart attack, that's very, very good. What's the problem with this is, let's say you're only interested in people who are 70 years old. So in your total, the distribution of patients, you might just have very limited number of people who are that years old, and therefore, or maybe even none, maybe you don't have anybody in the control group who is like 70 years old exactly. So therefore it's or even, smoker or non-smoker, maybe, it's like age, you can say, oh yeah, I can bucketize the age, so I will have some people there, but at the same time, like, bucketizing loses some resolution, and at the same time it will still reduce the number of samples by quite a lot. So what we are doing here is we are learning the relationships between features and outcomes, and we are creating for that the treatment and control response functions. So pretty much what that is we are creating models who use these conditions as features, and using these conditions as features, we can calculate the probabilities, so the estimates of the outcomes. The individual treatment effect is pretty much this. This is the last idea, just taking a little bit further, one step further, and it says that we can calculate the treatment effect for any individual. We can predict the treatment effect for each patient. It's of course much more useful than just the regular average treatment effect. It of course requires machine learning models to be able to make predictions, and we are using patients' features to of course compare the effect for them specifically. So to do that, there are two ways how to do it. We have a two-tree method or a single tree method. I'm not sure, I think initially they only use decision trees, but it can be any model, and therefore it's usually called, or I guess sometimes called, T-learner and S-learner. So T-learner is can be any model. Pretty much your objective is to get the best estimate for the same patient with the treatment and without the treatment. So that's, you have to basically have two models for that, one treatment model, one no treatment model. So they can have different architectures. Those, if you remember from the last presentations, those would be the prognostic models. So artificial intelligence for medical prognosis, yeah, that's the thing which we talked about. So I mentioned two tree models. Now let's talk about the single tree model. So what's good about the single model is, first of all, you don't have to train two models. That's very powerful. The second thing is your group, your sample size is pretty much double, because you don't have to, in the T-learner, you have to split the model in the treatment and non-treatment groups. So each of the model gets half the data. Here you're just using additional feature, presence or absence of treatment, so just another feature, and you're using a single model for that. I mean, for me, what's quite funny is that we are doing a lot of these things in just regular machine learning, but we don't have the names for that. It seems that in medicine, like what's interesting for me is that everything has its own special name, which you have to know. So that's one my personal like interesting experience. The question is, how do we evaluate our estimators? So of course the treatment effect, first fact, the treatment effect is not directly observable. We cannot apply the treatment for the same patient and not apply the treatment for the same patient. That's just, you know, impossible. What we can do is we can find a patient with very similar features who didn't receive the treatment, or we can find a patient with very similar ITE and compare the outcomes for them. So therefore, in this case, we know that so for this patient, we had like very similar scores, but the patients were very like their let's say age was different, and therefore we know that age like is not really impacting the estimation too much. Or if we find the like patient with very similar features, we can check like what's the treatment effect in this case. The final thing is C for benefit. If you remember from the previous lessons, that's actually quite similar to the C index. So we compare our estimates versus outcomes, and if you remember, we are calculating it based on the concordant, non-concordant, and risk-dice pairs. So concordant is then your treatment actually had positive effect, non-concordant when it had like no effect, like negative effect, risk-dice when your risk score, like your ITE, was exactly the same, and the outcomes were different. So in this case, like the calculation of the formula is exactly the same. You just divide your concordant pairs and half of the risk dice by everybody, by all the pairs, and you get your C for benefit. Now let's move to the medical question answering. So what's I guess good in the medical question answering is that you're working with exactly the same models as before. You're using Elmo, BERT, ExcelNet, whatever, like Albert, Roberta, GPT-3, whatever you happen to be using at work. Of course, you're not using GPT-3, but you can use like whatever model you want. You're dealing with exactly the same thing, like just regular NLP, tokenization, getting word embeddings. What's important is that right now, then when we have transformers, we have contextualized word representations. So your words depend, the meanings of your words depends on the context. We are not just like word back or glove. What we didn't have was the context. We didn't care about the context, and transformer models have this contextualized word representations. One, like the key thing in question answering is you have to say like what's pretty much you have to predict what like what's the index of a word which starts the answer, and what's the index of the word which ends the answer. So if I ask you a question and you have a corpus of text, you're going to say, yeah, the answer starts at index 55 and ends with index 86, and that would be your like selection of the answers. So how do you do that? You pretty much predict the probability of the start, and you predict the probability of the end for each word, and you pretty much calculate your the upper triangle of this matrix. So if you like put all the words in a corpus in a matrix, and like they are going in like just regular direction, a regular sentence, and you're calculating, so what's the probability of each word being the start of the answer, and what's the probability of each word being the end of the answer, and you only need to calculate the sum of these scores to know which one is your selected answer. One difference here between training regular QA models and training medical QA models is you are fine-tuning. Usually you're starting your training on something like Squad, and like when you have this general purpose question answering model, you are going to fine-tune it on a special medical data set. One important thing in machine learning, like natural language processing in medical like treatment, is label extraction. So how do you know if you're going to get pretty much how do you get the labels? Yeah, and this label extraction has various, like you can use a lot of ways how to do that. Getting it from like a radiology report is like one way, and how do you do that? Pretty much you check if some kind of disease is mentioned in the radiology report, and is the observation present or absent. I made a mistake, not of absent, but or absent. So here what it means in practice is you have a report that says like, oh, the person does have like pneumonia, or they have like this I don't know, cancer in the lungs. If they what you can do is you can or they don't have it, it might say that. So first of all, you have to detect all the keywords, and once you detect the keywords, you have to understand from the sentence, are we present or are we absent here? So in this case, what's really cool is that you can use SNOMED CT for synonyms. So there are like a lot of ways how in medical literature certain diseases are called, and in addition to that, you should check for subtypes. So sometimes you have you need to detect lung diseases. Like, does this patient have a lung disease? And it might say, yeah, that person has infectious pneumonia, and that would be a type, like a subtype of a lung disease. So you need to check for all the subtypes of lung disease, and like all of them would be would mean that you have this observation mentioned and present. So how do you evaluate your label extraction? First of all, you need to get the ground truth, and to get the ground truth, there are, like, again, multiple ways to do that. The main ones are either annotating the report itself, so the radiologist take the report and annotate it, stating that, yeah, from the report it says that we are present or absent. Or they can take the image itself, if it's like from a medical image, and annotate the medical image. And of course, we are using the usual metrics: precision, recall, F1 score, to indicate how good are we at identifying, like how good our model label extractor is at identifying these things. Oh, we had that already. Interpretation or interpreting machine learning models. So first of all, we need to decide on the global feature importance, or I guess that, like, the start would be determining the global feature importance. There are two ways how to do that. So first way is the drop column method. The second one is the permutation method. So the drop column method says that you drop each feature, and you pretty much build a model for their remaining features. So that would mean that you would have to build a model for each feature dropped. And the second one, permutation of shuffle method, says that you shuffle each column, so pretty much making it non-predictive at all. And you don't have to retrain the model, you just have to predict using the same data set that just shuffled column, or the shuffled feature column. By the way, this was the trick. I don't know, I learned it from FastAI, I think a couple of years ago, and I thought that's like seriously cool thing. Only right now it's like becoming more popular outside of FastAI circles. And like, I mean, the permutation method, it's so, I imagine if I wouldn't know this model, I would have spent so much time wasting my time on training these hundreds of models, which have no, you don't need to train them if you can just shuffle the column and see the feature importance there. So that's advanced feature importance. Checking or advanced checking for advanced feature importance. What happens if you need to know not feature importance in general, so not this global feature importance, but what happens if you want to know feature importance for each particular subject or for each particular patient? So one way is, again, to use the drop column method, is to build multiple models, so one per feature. By the way, this doesn't mean build a model with one feature, that means build a model without this feature. And what you do then is you go ahead and use this model to estimate the values for this particular person only, and then you check how important is this feature for prediction. What's the problem with this approach is, again, you have to build a lot of models. The second thing is it's very susceptible to correlated features. So that means that your models are not going to be much worse, because let's say you have two correlated features, so we're just going to use make the other feature say that it's much more important, and it's going to use that other feature a lot. And it's pretty much very much makes sense when you think about it. If I can predict something, you give me two features and I can use either to predict something, I am going to say that, yeah, the other one is not important, only the first one is. So you might be losing or saying that the feature is not important, then in fact it is. So how to do that, how to mitigate this problem? You can use Shapley values. So Shapley values is the average of all combinations with and without this feature. So if you thought that one model per feature is bad, so Shapley value has this combinatorial explosion, where you have to build for each feature, you have to build every single combination with and without this feature. So it might be, if you have 3 parameters, you are going to build, and let's say you have 3 features A, B, and C. So you're going to compare ABC versus AB, AC versus A, then C versus no features. So then what happens when you have a model which has to have no features? Very simple, you just predict the mean, the average, and compare this one feature with the average. So Shapley values have a lot of problems. There are modern alternatives that don't require retraining. So the most popular of them is SHAP. So actually I don't remember what this abbreviation stands for, but the S is for Shapley. And of course it's made to look made to look like SHAP. So if you are, don't worry, I mean, you don't have to actually build a lot of these models. There are some tricks how to get around that, but the main idea is that you have to compare every single model with and without the feature, and then average it, and therefore you know how important this feature is. If you happen to work with the deep learning models, one of the most, and especially images, one of the most useful tool is Heatmaps. So at least those who have participated in the AI bootcamp, we have done that in practice. We have used the gradient weighted activations, and you take a convolutional neural network architecture, so ResNet, Inception, Exception, one of those. You run your model using any sample. Then what you do is you take the last layer, which is the last layer before the flattening or the global before the global average, and you visualize the gradient. You multiply it by the gradients, and you visualize them. You scale them up. You overlay them on top of the image which you used, and you can see that the activations there are going to become the high activation values are going to show you where the model is paying the most attention. One thing which, don't forget, which I haven't mentioned right now is, in this case, don't forget to apply ReLU. So therefore you don't ignore the negative values and only deal with positive values. And finally, these are the resources which I used and which I checked while doing the course. Again, this whole thing was based on my learnings on the course AI for medical treatment, and the whole specialization, AI for medicine specialization. So my takeaway, I was actually, before doing the specialization, I was, I guess, overly excited, because the deep learning specialization, that was an amazing thing. I was one of the at that point I was really in this very active mode on learning artificial intelligence and machine learning, and this provided me with an amazing resource. I guess that still is one of the very good starters resources, the deep learning specialization, and I was expecting the same thing for medicine, but unfortunately it's not as good in my opinion. By the way, don't take me wrong, I learned a lot and I liked the specialization, but it wasn't as groundbreaking as the AI for deep learning or the deep learning specialization. So that's my, I guess, last message. It was still interesting. I still learned a lot, and it was still useful. These are the resources about the which I checked out for making this presentation. Now it's time for the question answering. So if you have questions, please use the link at the top and write your questions there. So let's start with the first question, going from Arnas: how to connect AI and robotics with medicine? Machine learning and data analysis do not help that much. That's a good question. Unfortunately, I have zero experience with robotics. I would say maybe at the end of this presentation, I'll suggest you to maybe, in my opinion, talk with people who are specializing with robotics, explain your problem, because it's there are so much things how you can do. You can have a lot of robotics and a little bit of AI, and vice versa. So it depends what's the ratio of this hardware and software which you're thinking of. So that's the only question so far. I'm going to give you a couple of minutes to write more questions. questions appearing. Guess we can move forward and today's presentation. If you have questions later, let's put this discussion offline. Let's use the Tribe of AI platform. We can discuss this presentation later, or what's your idea? What are you going to try to solve with medicine and artificial intelligence? So I think it's a very, very great niche. We can achieve so much there, and we can do so much good in this area. So I hope like this series was a little bit of an inspiration to you. I hope that you're going to at least think about using AI in medicine. So thank you very much for being there, and see you next time. Bye bye.